Hello and welcome to the Unit 8 Section 2 video on function operations. So before we get into actually doing a lot with this, let's just talk a little bit about what the basic operations mean and how they're notated. So you can perform operations on functions in the same way that you perform operations on numbers or expressions. You can add, subtract, multiply, or divide functions by operating on their rules. So here we're really going to take some of these things that you've seen but not necessarily worked with very much, and we're going to start using the notation. So the notation I'm talking about is f of x. You know, f of x is another way of writing the variable y. You have f of x equals, and then you go into what your function is. Well, here what we're going to do is we are going to talk about how you do operations on f of x, the thing itself, okay? So let's talk about f and g being any two functions. You have a function h that can be defined by performing any four basic operations on f and g. And those operations are addition, subtraction, multiplication, and division. So let's take a look at this table and let's talk about what these things mean, okay? So we can take f plus g of x, we can add the f function and the g function together, and this simply means you're just adding the two functions, okay? That's all it really means. This is simply a condensed way of saying f of x plus g of x. F plus g of x is the same as f of x plus g of x, okay? So what does that look like? Well, in this case, our combined function, which we're calling h of x, is going to be 5x, because that's our f of x here, and we're going to add it to our g of x, which is x plus 2. Well, all you have to do is now add the parts. 5x plus x gives you 6x, and then you have plus 2 on the end. So when you add f of x and g of x as they are defined here, you get 6x plus 2 as your h of x, which is your combined function. You can similarly do the same thing with subtraction. You've got h of x equals f of x minus g of x. And this is where you have to be very careful, because remember, this minus sign distributes. So we have 5x minus x minus 2. 5x minus x gives you 4x, and then you have minus 2 on the end. Now when we get to multiplication, f times g of x is simply f of x times g of x. So if we do that, we simply multiply our two parts, f of x being 5x and g of x being x plus 2. So all you're going to do is multiply your 5x to the x and 5x to the 2. So that's going to give you 5x squared plus 10x. And then finally, in division, we have f divided by g of x, which is the same as f of x over g of x. So remember, g of x cannot be equal to 0 because we can't divide by 0. That's the one condition that we have to add in for division, which is a pretty simple condition. You know that. You can't divide by 0. So let me write this a little bit down because we're going to be working with fractions here. H of x equals f of x divided by g of x. Well, f of x in our example is 5x, g of x is x plus 2, and that's simply all we can do with it. There's nothing we can do to simplify that. So that would be your answer, but you have to specify that x cannot be negative 2 because we cannot divide by 0. Okay, so now you've seen a little bit about how it works. Let's do some examples. So given f of x is 2x squared minus 5x minus 3, and g of x equals x squared minus 4x plus 3, let's perform these indicated operations. So let's begin with f plus g of x. Well, we know f plus g of x is f of x plus g of x. So all we have to do is take f of x, which is 2x squared minus 5x minus 3, and g of x, which is x squared minus 4x plus 3, and we add these two things together. So now all we have to do is combine our like terms. So 2x squared plus x squared gives us 3x squared. Negative 5x minus 4x gives us negative 9x. And then negative 3 plus a positive 3 gives us 0. So that's all we're left with. For f minus g of x, we simply take f of x and then we subtract g of x. Now remember, this time we have to make sure we distribute the minus, and we'll do that as we collect like terms. 2x squared minus x squared gives us x squared. Negative 5x minus negative 4x gives us negative 5x plus 4x, which is simply minus x. And then negative 3 minus 3 gives us negative 6. And then for this last one, we have g of x minus f of x. And this one was written out in that form. Remember, you're going to see this in different ways, okay? So this one, we're going to take our g of x first, and then we're going to subtract our f of x. And you're going to see this kind of property of polynomials. When you flip which way we subtract, I think you're going to see a pattern here. X squared minus 2x squared gives us negative x squared. Negative 4x minus negative 5x, so negative 4x plus 5x gives us x. And then 3 minus negative 3 gives us 3 plus 3, which is plus 6. So you'll notice when we flipped our f and g around, we just ended up with opposite signs on every term. And that will work for polynomials when you have two polynomials for your f of x and g of x. All right, so recall what your f of x and g of x are from the previous page, because we're going to do a few more examples using those. In fact, I will go ahead and write at the top here what those are. So I've placed those two equations, or those two functions, at the top for you for reference as we continue on here to keep us from flipping back and forth. So let's do g of x, or g times f of x, okay? So this is going to be g of x times f of x. So g of x is going to be x squared minus 4x plus 3. F of x is going to be 2x squared minus 5x minus 3. And we're going to multiply these two things together. So this is going to take just a little bit of making sure you keep track of everything that you're multiplying. So what I like to do is start with this x squared term, and we're going to multiply this x squared term out to all three of these. Then we'll move to the middle term and multiply it out to all three. Then we'll end with the last term and multiply it out to all three. So when we do that, we get x squared times 2x squared, which gives us 2x to the fourth. Then we get x squared times negative 5x, which is negative 10x to the third. Then you get x squared times negative 3, which gives you negative 3x squared. Now we move on to the middle term. Negative 4x times 2x squared gives you negative 8x to the third. Then you have negative 4x times negative 5x, which gives you positive 20x squared. Remember, both of these had x's on it, so that's where you have to be very careful to make sure you don't lose anything along the way. Negative 4x times negative 3 gives you positive 12x. Then the last term, 3 times 2x squared gives you 6x squared. Then 3 times negative 5x gives you negative 15x. And then finally, 3 times negative 3 gives you negative 9. And then from here, we're just going to collect the like terms. 2x to the fourth stands alone. Everything with the x to the third. We got negative 10x to the third, and we got negative 8x to the third. So that's going to give us negative 13, or I should say negative 18x to the third. Actually, this is again where you have to be very careful. Let's go back and check our work here. We have 10x to the third from here. We have 3x squared from here. That's fine. 4x, so that gave us the third here. And we have 4x, that's squared, and then this one gives us an x, and then that. So we're all good. 18x to the third. So again, you want to make sure you double check your work as you go along, because it is easy to make a mistake when you're dealing with this many terms. Now let's collect our x squared terms. We have a 3x squared, or negative 3x squared, a 20x squared, and a 6x squared. So all of that together is going to give us a positive 23x squared. Now let's take care of our x's. You got 12x and negative 15x. That gives us a negative 3x, and then we have this negative 9 on the end. So you'll notice that we had a lot of terms to take care of. One thing that you may find helpful is as you go along, as you finish collecting terms, cross them out. As we did the x to the thirds, cross those out after we did those. X squared, you cross those out after you do those. And then from the x's, you cross those out after you do those, and then we finish off with the 9. So you may find that to be a useful strategy as you're collecting like terms to make sure you don't miss anything. Okay, let's move on to example E. F of x divided by g of x. Well, that's going to be f of x, which is 2x squared minus 5x minus 3, divided by x squared minus 4x plus 3. And then from here, we are going to factor the top and the bottom, because when you divide, we need to see if there's anything that's going to cancel. Now the top, you're going to have to find two numbers that multiply to give you negative 6 and add to give you negative 5, and then split the middle term and factor by grouping. I'll let you do that on the side, and I'll give you the answer so you can check your work, which is 2x plus 1 times x minus 3. On the bottom, this one's a little easier to factor. Two numbers that multiply to give you 3, add to give you negative 4, and that would be negative 1 and negative 3. So we can cancel the x minus 3 terms, and that leaves us with 2x plus 1 over x minus 1. Now remember, when we divide, we have to specify what x cannot be. And there's two values that it cannot be. It cannot be 1, and it cannot be 3. So even in what you cancel, you have to include that as x values that do not work. All right, for f, we have g divided by f of x, which is simply g of x divided by f of x. So we're going to be doing the flip of what we just did. X squared minus 4x plus 3 divided by 2x squared minus 5x minus 3. The good thing is these factor just the same as they did before. So once you factored it in the previous one, you don't have to go through that work again. You can just simply write down what the factorization is. We know that x minus 3's will cancel, and so you'll end up with x minus 1 over 2x plus 1. And in this case, x cannot be negative 1/2, and it can't be 3. Now that we've done some operations on functions, let's talk about composition of functions, because you can have functions nested within one another. So another function operation that uses the output from one function as the input for a second is a composition of functions. So here's the definition. We have f of g of x. Okay, so it's not a multiplication symbol. We actually have a little open dot that's in between. That's a little O that kind of reads f of g of x. And you can write it into one of two ways. You can write it as f open dot g of x, or you can write it as f of g of x, where g of x is inside of your f function. Okay? Now, the domain of f of g includes all the elements of x in the domain of g, for which g of x is in the domain of f. And we're going to talk a little bit more about the domain here shortly. But let's talk about what f of g means. So let's look at this diagram. We're going to use this diagram to find f of g of 1. Okay, so f of g, we go from here all the way across. So we go and do our g operation. This would be g of x. And then this would be f of x. And f of g of x takes us all the way from the beginning to the end in one go. But you need this intermediate step to get there. So if we're looking for f of g of 1, well, we start off with g of 1. We can write this as f of g of 1. Okay? And that's what we have down here. But I'm going to write it up here as well for you. So if you have f of g of 1, first we need to find what g of 1 is. So we go to 1 on g, and we find g of 1 is 4. So we know if g of 1 is 4, we can put that in for g of 1. Now we're looking for f of 4. Well, f of 4 is 8. So therefore, we end up with 8. And this is what this explanation gives us. We find g of 1 first, which is 4. Then use 4 as the input into f. f of 4 equals 8. So if we wanted to find f of g of, say, f of g of 5, then we would follow this line. We start with g of 5, which is 8, and then f of 8 is 16. The order of function operations is the same as the order of operations for numbers and expressions. To find f of g of 3, evaluate g of 3 first, and then substitute the result into f. Okay, so remember, we're kind of working with parentheses here. You do the inside first, and then go to the outside. All right, let's do some examples of this. Here we're given a set of ordered pairs that define f, and a set of ordered pairs that define g. And we're going to evaluate the composition. So, f of g of 2. Well, we know that we can write this as f of g of 2. So what's g of 2? Well, let's see. G of 2 is 3, because 2 is our x, 3 is the y, that is our output. So then we have f of 3. If we go to f of 3, that's going to be 4. G of f of 3. Well, f of 3 is 4, so that gives us g of 4. G of 4 is 3, and so our answer is 3. For this one, g of f of 1, that's g of f of 1. F of 1 is 2, so we substitute that in. G of 2 is 3. And then finally for D, this is f of g of 6. So we go and find what g of 6 is, which is 1, and then f of 1 is 2. So it's all about following the breadcrumbs in problems like these. So now that we've done it with some numbers, let's move on and do it with some functions. So let's start with these two functions, or actually we're given three functions. Let's start with h of g of 2. Well, first we're going to do g of 2, because that's going to be our innermost part. Well, g of 2, we're going to substitute 2 in for x here. We get 2 squared minus 3 times 2 plus 6. And then when you do that math, you can simply put it in your calculator if you like. You're going to end up with 4. So now we go to the outside part. H of 2, or actually I should say H of 4, because that was our value for G of 2. We're going to go to H, put that in for our X. And when we do, 4 times 4 is 16, minus 1 is 15. So H of G of 2 is 15. All right, let's do B. F of negative 10. So we're going to start with f of negative 10 on the inside. We're just going to put in negative 10 for x. Negative 10 plus 7 gives us negative 3. So now we're going to do h of negative 3. We just plug that in for our x. 4 times negative 3 is negative 12, minus 1 gives us negative 13. For h of g of x, we're going to start with, now you notice we don't have a number this time, we have an x. Well, we know what g of x is. G of x is this function. So now we're going to evaluate h of x squared minus 3x plus 6. And to do that, you're simply going to take what g of x was, you're going to substitute this whole thing in for x in our h function. So everywhere there's an x, you're going to put what is in here. And now we just simplify. We multiply out our 4. And then we collect our like terms. And that is our final answer. This is what h of g of x is in terms of x. So we could use this if we wanted to find out what any h of g of x is for any value of x. We can just simply plug it into here rather than doing the 2 steps. So that's where that becomes a little bit more useful. Instead of doing 2 steps every time, we've now turned it into a 1-step problem. Let's do g of h of x. So now we're going the other way around. So h of x we know is 4x minus 1. So we're going to do g of 4x minus 1. Well, now we're going to plug into g. Everywhere there's an x, we're going to put 4x minus 1. So we have 4x minus 1, quantity squared, minus 3 times 4x minus 1, plus 6. So this we're going to expand. You can write it as 4x minus 1 times 4x minus 1 and do the FOIL method. When you do, you get 16x squared minus 8x plus 1. Here we're just distributing the negative 3, so we get negative 12x plus 3. And then we have our plus 6 on the end. And then again, we're just collecting like terms. 16x squared, negative 8x minus 12x gives us negative 20x. And then 1 plus 3 plus 6 gives us 10. And then finally, for E, we're going to do 3 of these. H of f of g of x, okay? So you start from the innermost one, and then you work your way out, and then you work your way out again. So we know that we have h of f of g of x. Well, g of x we know is x squared minus 3x plus 6. And now we're going to do f of this, okay? So to do that, we are going to plug in for everywhere that we have an x, we're going to plug that in for x. So here you're going to have x squared minus 3x plus 6, and then the other part of that function is plus 7. And here you can actually go ahead and group the 6 and 7 together. That makes 13. And now we're evaluating h of x squared minus 3x plus 13. So we go into our h function. Everywhere there's an x, we substitute that in. So a lot of this is just substitution. You substitute in the values and then you simplify. You substitute in your polynomial and you simplify. 4 times 13 is 52. And then we collect that 1 in with the 52 on the end. And so we end up with plus 51. All right, so that's some examples of how to do this with nested composite functions. Now let's talk about the domain of these functions. Recall that the domain is all possible values of x that you may put into a function. Okay, that's just what the definition of domain is. It's all the values of x that we can use. Remember, in rational functions, we threw out one of those values of x because we had an asymptote, because that made the bottom 0. So the domain is any values of x that you can put into a function. The domain will always be negative infinity to positive infinity, except for 2 situations. And we've hit both of these situations already. So this is a bit of a review, bringing it all together. When x is in the denominator, as I just mentioned, you end up with the asymptote. Or when x is under an even radical, because remember, you cannot take an even root of a negative number and get a real result. So therefore, that cuts the domain down for those as well. So let's talk about finding the domain, knowing a little bit of this information. So we're going to perform the operation given that f of x equals 4x to the 1/2 and g of x equals negative 9x to the 1/2. We're going to state the domain and the resultant function. So remember, x to the 1/2 is just another way of writing the square root of x, and that's how I'm going to write it here. So we have f of x, which is 4 square root of x, plus g of x, which is negative 9 square root of x. Well, you can add those fairly easily. You have 4 plus negative 9, that's 4 minus 9, which gives us negative 5 square root of x. So that's our resultant function. What is the domain of this? Well, the domain of this, we know we can't have a negative number under the square root, so our domain is going to be all values of x that are greater than or equal to 0. You can also write this as 0 to infinity, where you include the 0, because you can take the square root of 0. It's just 0. All right, let's do the next operation where we subtract. So we have 4 square root of x minus negative 9 square root of x, and that gives us 13 square root of x. And again, you can't have the square root of a negative, so x is going to be greater than or equal to 0. You can also write it in interval notation as that. All right, now let's talk about the last topic, which is division of functions. So to divide functions, you're going to plug in the functions, factor each one separately, then cancel out any common factors. We did a bit of this when we covered rational functions. That's going to be no different. Now remember, everything in the parentheses must cancel, not just one part. Okay, so if you have x plus 2 over x plus 3, you can't cancel those x's because the plus 2 and the plus 3 are attached. Okay, so we're going to perform the operation given that f of x equals this and g of x equals this. Then we're going to state the domain of the resultant function. So g of x over f of x, this is going to be x squared, or x minus 2, or x plus 2, over 4x squared plus 8x. Now we are going to factor the bottom. So that gives us 4x, factors out, and then we have x plus 2. And so we're left with 1 over 4x. So our domain is all x's except x cannot be 0 or negative 2. And again, you can write that in interval notation as negative infinity to negative 2, union with negative 2 to 0, union with 0 to infinity. For b, we have just the flip. We've got 4x squared plus 8x on the top, x plus 2 on the bottom. It factors just the same. The 4x comes out of the top, and the x plus 2's still cancel, but now our result is 4x. This time the domain only has to exclude the negative 2, because we ended up with the two pieces on the top rather than on the bottom. All right, now we're going to do a couple more examples, this time with multiplication. And we're using these two functions now for these two examples. So we're going to do f of g of x. So we're going to do f of g of x is 3x squared minus 5. And when we plug that in for x in the f function, we get 2 times 3x squared minus 5. We distribute the 2 out, we get 6x squared minus 10. And our domain, since this is just a polynomial, there's no radicals, there's no fractions, it's just negative infinity to positive infinity. Now let's do g of f of x. So we do f of x first. F of x is 2x, and so that gets plugged in for x everywhere there's an x in the g function. Oops, minus 5 on the end. So 2x goes in place of x, and then you have minus 5 on the end. So you have to do the square first. Remember, exponents before multiplication. So 2 squared is 4, x squared is x squared, and so the result you end up with is 12x squared minus 5. And again, this is just a polynomial, so the domain is all reals. All right, so that's it for section 2 of Unit 8, where we talked a little bit about how to do function operations and how to add functions and subtract functions, multiply and divide, and then how to do composite functions as well. As we move on into section 3, we are going to talk about piecewise functions, which are functions that have different types of properties given what the domain is or what that interval is along the domain of the function. So we'll talk about that coming up in the next section.